The 555 timer IC is an integrated circuit used in a variety of timer, delay, pulse generation, and oscillator applications. It is one of the most popular timing ICs due to its flexibility and price. It was designed in 1970 by Hans R. Camenzind under contract to Signetics Corporation. Today, half a century later, it is still an immensely popular circuit building block. According to Camenzind, the idea for the new IC came from the work he did at Signetics on the phase-locked loop. He had needed an oscillator whose frequency could be set by an external resistor and a capacitor, and was not affected by changes in either supply voltage or temperature. The IC was first marketed in 1972 and it had immediately a huge success. In his book, Camenzind tells he had deliberately made the design flexible, but 9 out of 10 applications were in areas and ways he had never contemplated. For months he was inundated by phone calls from engineers who had a new idea for using the timer. In this video we see the 555 internal schematic in great detail and how it works in Astable mode. The 555 has 3 operating modes. In Astable mode, the 555 operates as an electronic oscillator. Uses include logic clocks, LID and lamp flasher, pulse generation, tone generation, security alarms, and so on. In bistable mode or Schmidt trigger, the 555 operates as a flip-flop. In monostable mode, the 555 functions as a one-shot pulse generator. Applications include timers, missing pulse detection, bounce-free switches, touch switches, frequency divider, and so on. There are a lot of good videos about 555 projects and applications, but I didn't find any describing the internal schematic, so that is what this video is about, a deep look in the internal schematic of the 555. But before to dive into the circuit description, we follow the explanation Camenzind himself gave in his book, Design Analog Chips, about the birth of this iconic circuit. According to Camenzind, the idea for the new AC came from the work he did at Signetics on the phase-locked loop. He had needed an oscillator whose frequency could be set by an external resistor and a capacitor and was not affected by changes in either supply voltage or temperature. Several products resulted from the basic design, among them the 566 voltage-controlled oscillator. What he first proposed to Signetics was this circuit, modified so it could also be triggered and produce a single cycle only, i.e. it would be both an oscillator and a timer. Let's see the general working of this circuit, because here we have the basic idea of the 555-2. As you can see, we have a voltage to current converter which takes the input voltage of 5.6 VCC to the pin R where an external resistor is connected. So across this resistor drops 1/6 of VCC and we have a constant current of VCC over 6 Rx. This current goes to charge the external capacitor Cx. Being the current constant, the voltage across the capacitor raises linearly. The two comparators have an input connected with the external capacitor and the other input connected to the voltage divider. So if the voltage across the capacitor is less than VCC divided by 3, then the positive input of a comparator 2 is at higher voltage than that of the negative input. So the output of the comparator 2 is high, putting high the reset input of the flip-flop and producing a low value in the output of the flip-flop. This low output leaves the switch as it is, keeping the current charging the capacitor. When the voltage across the capacitor exceeds 1/3 of VCC, the output of comparator 2 goes low, but the flip-flop keeps the previous low state, so nothing changes and the capacitor keeps charging. When the voltage across capacitor reaches 2/3 of VCC, the first comparator goes high, the set input of the flip-flop goes high, and so the flip-flop output, flipping the switch and making the current go into the current mirror, which copies this current to the other branch, discharging the capacitor. When the voltage across the capacitor goes down below 2/3 of VCC, the output of comparator 1 goes down, but this doesn't affect the output of the flip-flop, which remains to the high value, keeping the capacitor discharging. When the voltage across capacitor reaches VCC divided by 3, comparator 2 goes high, making flipping the switch and the capacitor is charged again, starting over the cycle. So the voltage across the capacitor oscillates between 1/3 of VCC and 2/3 of VCC, and being the current constant, the voltage raises and decreases linearly. To find the oscillation frequency, we keep in mind the relationship between voltage and current in a capacitor. Being the current constant, we can write this relationship where delta V is the maximum voltage drop across the capacitor and delta T is the charging time. Sorting things out, we get that the charging time is 2Rx-C, and being the discharging time equal to the charging one, we have an oscillation period of 4Rx-C. The frequency is this, and you see it is independent of the power supply VCC. You see both the current and the amplitude of the oscillation are related to the power supply and they cancel each other out. The 566 is a voltage control oscillator because by changing the voltage in this node, we change the current charging and discharging the capacitor, thus modifying the frequency. According to Camenzind book, he proposed to Signetics this circuit modified so it could also be triggered and produce a single cycle only. The project almost didn't get off the ground. The engineering staff didn't think much of the idea. Timers at the time were put together from an op-amp or comparator and a few discrete components, including a Zener diode or two. They argued that such a design would cut into the sales of their present ICs. Just the marketing manager Art Fury supported him, giving him a year contract to deliver the circuit. The 555 was first marketed in 1972. According to the description in this datasheet of 1973, the 555 monolithic timing circuit is a highly stable controller capable of producing accurate time delays or oscillations. Additional terminals are provided for triggering or resetting if desired. In the time delay mode of operation, the time is precisely controlled by one external resistor and capacitor. For a stable operation as an oscillator, the free running frequency and the duty cycle are both accurately controlled by two external resistors and one capacitor. The circuit may be triggered and reset on following waveforms, and the output structure can source or sink up to 200 mA or drive TTL circuits. As you can see in these block diagrams, the core of the circuit remains the same. We have a 3-5K voltage divider, two comparators, and a flip-flop from which we take the negative output. In the 555 we have in addition an inverting output stage which can provide up to 200 mA, the possibility to reset the flip-flop, a discharge input connected to a BJT driven by the negative output of the flip-flop, a control voltage input, the threshold and the trigger inputs, and of course VCC and ground inputs. We have 8 inputs, and this has been possible because Camenzind deleted the voltage to current converter which he used to linearly charge and discharge the capacitor in the 566. Camenzind removed the converter when he realized that a linear relationship between current and voltage was not needed to obtain the cancellation of the power supply from the oscillation frequency formula. In this way, the pins from 9 decreased to 8, and he could use a 8-pin package. Otherwise, he would have been needed a more expensive 14-pin package. Here you see the 555 in Astable mode configuration, so producing an oscillation. The working principle is similar to the 566, but we don't have the constant current anymore. So let's say initially the capacitor is at 0 volts. Comparator 2 is connected to VCC divided by 3, and comparator 1 has the negative input connected to 2/3 of VCC. So the output of comparator 2 is at high value, putting high the set input of the flip-flop, thus producing a 1 in the Q output and a 0 in the negative Q output of the flip-flop, which is the output driving the discharge BJT and the inverting output stage. This means that the Q14 BJT is off and the output is at 1. In this situation, the voltage supply charges the capacitor through R1 and R2 in the typical exponential way of the RC network. To work properly, the current in the external network has to be enough to feed also the threshold and the trigger inputs. For this reason, the datasheet considers 20 MΩ as the maximum value of the external resistances R1 and R2. We'll explain better this item in the schematic analysis. When the voltage across the capacitor reaches and exceeds VCC divided by 3, the output of comparator 2 flips to 0, but the flip-flop output remains unchanged, because the flip-flop keeps the previous value even when the set input goes back to 0. So the capacitor keeps charging. Comparator 1 remains at 0 till the positive input connected to the capacitor reaches the negative input at 2/3 of VCC. At this point, comparator 1 flips to 1, giving the reset to the flip-flop, turning on the negative Q output and switching to 0 the 555 output. The negative Q output at 1 switches on the BJT Q14, connecting the discharge input to ground, discharging the capacitor through the R2 resistor. So the capacitor is charged through R1 and R2 and discharged only through R2. When the voltage across the capacitor goes below 2/3 of VCC, comparator 1 goes low, but the flip-flop remains unchanged. When the voltage across the capacitor reaches VCC divided by 3, comparator 2 goes high, giving a set pulse to the flip-flop, which goes low, switching off Q14 and putting the 555 output to the high value. At this point, the capacitor starts charging again and the cycle is repeated. So the capacitor is charged from VCC divided by 3 to 2/3 of VCC via R1 and R2, and it is discharged via R2 from 2/3 of VCC to VCC divided by 3. The output is at high value in the charging time and at low value in the discharging time. So if we had an RC network like this, the current is equal to this and also this. So the equation for the charging of the capacitor is this, and it has the solution where we find B imposing the boundary condition that at the time 0, V as function of t is equal to VCC divided by 3. Finally, we get the equation describing our charging capacitor. The charging time stops when the voltage is 2/3 of VCC, so we get this equation, and sorting things out, we get that T charge is 0.693 times R1 plus R2 times C. The discharging time is found writing the current equation in the circuit. Sorting things out, we get the voltage equation, which has this solution. Imposing the boundary condition that at time 0 V as function of t is equal to 2/3 of VCC, we get B and the equation of our discharging circuit. The discharging time lasts until the voltage reaches 1/3 of VCC, so we get this, and finally we find the discharging time, which is equal to 0.693 times R2 times C. So the oscillation period is this and the frequency is this. You see there isn't any relationship with the supply voltage, which has been cancelled out. The oscillation frequency depends only on R1, R2 and C. From the datasheet you see the accuracy is 0.5%. You see also the typical value of the drift with temperature is 30 ppm per degree C, and the drift with supply voltage is 0.05% every volt. The charging time is always larger than the discharging time. This means that the output is in on state longer than it is in the off state, so the duty cycle is always more than 50%. But taking R2 much larger than R1, we can get close to have a 50% duty cycle. It is not quite possible to achieve a 50% duty cycle. According to Camenzind book, charging and discharging the timing capacitor through a resistor connected to the output is not such a good idea. The high and low voltage drops are unequal and have significant temperature coefficients. The datasheet tells us we lose at least 1.7 volts in the high output swing and at least 0.1 volts in the low swing. But these data depend very much on the output current, as we'll see later in the schematic analysis. So for example, with a VCC of 15 volts, we would charge the capacitor with a voltage drop of 8.3 volts, but we would discharge it with a voltage drop of 9.9 volts. This means that this equation is wrong because considering the right voltage drop and solving the RC charging and discharging equations as we saw before, we would have this as charging time and this as discharging time, and they are clearly different. Another solution is this, where you can get any duty cycle, but of course you need additional components. This is the charging path and this is the discharging one. Since 1972, the 555 has been produced by many different manufacturers, so you can find many slightly different versions. This is the original version by Signetics taken from the Camenzind book. It has 25 transistors and 13 resistors. We didn't find on the web many descriptions about the internal schematics of the 555, but we found some clues not only in the Camenzind book but also in the Evil Mad Scientist's document and of course in the 1973 datasheet. First, let's recognize the blocks. Here we have the threshold comparator or comparator 1, which has one input connected to the voltage divider at 2/3 of VCC. This comparator is composed by a Darlington differential pair and an active load. Here the comparator 2, a trigger comparator, with an input connected to the voltage divider at 1/3 of VCC. This comparator is composed by a PNP Darlington differential pair and a resistor. This is the voltage divider composed by 3 5K resistors. There is a rumor stating the circuit was named after it, but Camenzind has explained several times that the name was chosen by the marketing division for whatever reasons. Here the flip-flop. It is very simple and it is composed only by one resistor and two transistors, Q16 and Q17. Working in saturation region. The flip-flop is controlled by the output of the trigger comparator through Q15 and by the output of the threshold comparator. Here the output stage. You see it is an inverting stage because it is driven by the collector of Q20 and it can provide up to 200 mA through the Darlington Q21 and Q22 and through Q24 with the help of Q23. For the high current level. Here the discharge transistor Q14, so important the oscillator mode, and here the reset circuit which imposes a 0 volt to the base of Q17, switching it off and forcing to the low state the output of the 555. Now let's review the general working in a stable mode with the insight of the schematic. We switch the power on and the capacitor starts to be charged through R1 and R2. So the first phase is when the voltage across the capacitor is between 0 and 1/3 of VCC. The threshold comparator has the base of Q4 at 2/3 of VCC, so much more than the threshold input, and the whole current flows in this branch of the differential pair. The current in Q8 is mirrored and amplified in Q7, from which it goes to ground. So the output of the first comparator, the collector of Q6, is at high impedance and doesn't affect the flip-flop. The trigger comparator has an input at 1/3 of VCC, so if the trigger input is less than 1/3 of VCC, the current flows in this branch of the differential pair. The voltage across R6 starts to increase, and when it reaches 0.7 volts, Q15 is on, drawing current from the collector of Q11. The current provided to the base of Q15 has to be enough to force it in saturation. When Q15 is in saturation, its collector emitter voltage is around 0.1 volts, switching off Q16. If Q16 is off, the current flowing in this branch goes into the base of Q17, switching it on and forcing it in saturation. Q17 now draws the whole current coming from the second collector of Q19, which is a current mirror copying the same current flowing into the base of Q17. Q20 is then off, letting the base of Q21 going up and switching on the output Darlington Q21 and Q22. The output is high. The discharging transistor Q14 is now off, because no current is coming from Q20. When the voltage across the capacitor is near 1/3 of VCC, the trigger comparator switches to the low state and stays low as long as the voltage across the capacitor remains above 1/3 of VCC. In this situation, the current flows in this branch of the comparator. The base of Q15 is at 0 volt because no current flows on R6, so Q15 is off, but since Q17 remains in saturation and Q15 doesn't need the current anymore, this node is kept at a low voltage, preventing Q16 to switch on, so Q20 is off. and the output is kept at a high value during the charging time of the capacitor, so till the voltage across the capacitor reaches 2/3 of VCC. If we assume the threshold comparator with no offset, when the voltage across the capacitor is at 2/3 of VCC plus 50 mV, all the current is flowing the left branch of the comparator. This current, mirrored amplified by the current mirror and the differential amplifier Q5, Q6, Q7, flows out from the collector of Q6 towards the flip-flop. If this current is large enough, it flows through R11, raising the voltage at the base of Q16. When the voltage at the base of Q16 reaches 0.7 volts, Q16 switches on, drawing current from the base of Q17, which switches off. Since Q17 is off, the base of Q20 goes high, switching on Q20. All the current from the second collector of Q19 flows into the base of Q20, forcing it in saturation. When Q20 switches on, starting conducting, the current goes to R15, creating a voltage drop across it. When the voltage drop across R15 is 0.7 volts, Q24 and Q14 switch on, drawing current from their bases and raising the voltage drop on R15. If Q20 provides enough current, Q14 goes in saturation, providing the ground needed to discharge the external capacitor through R2. In this situation, being Q24 on, the output of the 555 is low. The capacitor is discharged, and when the voltage across the capacitor drops of about 100 mV, the threshold comparator switches on again and the whole current flows in the right branch of the comparator. However, the flip-flop remains in the same state. A balance is reached, and this node is at about 0.8 volts and this at 1.5 volts. So a current flows through R11, going to the base of Q16, and it has to be enough to keep it in saturation. The capacitor keeps discharging up to 1/3 of VCC, so when the trigger comparator switches high again and the cycle repeats itself. As you see, the comparators switch at 1/3 and 2/3 of VCC, creating little high pulses to change the flip-flop state.
Let's see the threshold comparator. It is composed by a Darlington differential pair with a particular active load, composed by two current mirrors Q5, Q6 and Q7, Q8, plus another differential pair Q6, Q7, where you see Q6 and Q7 are part of both the current mirrors and the differential pair. We assume VCC equals 15 volts because in the datasheet many tests have this condition. In this case, 2/3 of VCC is equal to 10 volts and the voltage at the virtual ground of the differential pair is 8.6 volts, so the tail current is 0.86 mA. If the threshold voltage is below 10 volts, all the current flows in the right branch and it is mirrored in Q7 according to this relationship. The current in Q8 is equal to 0.86 mA, the whole tail current of the Darlington differential pair. So the current in Q7 going to ground reaches 4.9 mA. So this particular load provides current gain, which we use when the threshold input reaches 10 volts or a little more. In this case, the currents start to increase in the left branches up to 4.9 mA. This current has to be enough to force Q16 into saturation region. We'll see it better talking about the flip-flop. Because of the Darlington, the voltage unbalance needed to shift the current from a branch to another is 4 times the thermal voltage, so 100 mV. So we have this 100 mV around 10 volts in which the comparator goes high, providing current to the flip-flop and making it change its state. When the flip-flop changes its state, the discharge of the capacitor lowers the voltage at the threshold input below 10 volts and the comparator comes back to the previous state, in which all the currents flow through the right branches. So the comparator just gives a current pulse needed to change the flip-flop state. The differential pair is not well balanced, so there is an offset of around 30 mV. But considering the voltage swing, this is not a big problem. According to the datasheet, the base current has a typical value of 0.1 microamps and a maximum value of 0.25 microamps. This means a Darlington beta between 3400 and 8600. Which is not surprising. Moreover, this means that in the short time in which the comparator is high, we need a maximum base current of 0.25 microamps. So we must be able to provide this current from the external network, and this means that the external resistors R1 plus R2 must be less than 20 megaohms. Here you see the datasheet showing the maximum base current and the 20 megaohms limits.
The trigger comparator is composed by a PNP Darlington differential pair with an 100 kΩ resistor as load. The PNP Darlington allows the trigger input to be at ground level. The tail current is provided by a wattral current mirror, composed by Q19 and Q9. The current in this branch is this, assuming Q16 off and Q17 on, or this, assuming Q16 on and Q17 off. The tail current I9 is found solving this equation in iterative mode. When the voltage across the capacitor is below 5 volts, the currents flow in the left branches of the differential pair, so in R6 assuming Q15 off. The voltage in R6 increases, and when it reaches 0.7 volts, Q15 switches on, keeping the voltage on R6 at 0.7 volts. So most of the current goes into the base of Q15, and it has to be enough to force Q15 in saturation mode. If Q15 is in saturation, Q16 is switched off, and the flip-flop changes its state. The current in R6 is this, and then the maximum current to the base of Q15 is this one, and it has to be enough to force Q15 in saturation. Being the voltage across the capacitor oscillating between 5 and 10 volts, the trigger comparator gives a current pulse to switch Q15 on when the trigger voltage reaches 5 volts. So the trigger comparator has the output high just the time needed to make the flip-flop changes its state. However, according to the datasheet, in that moment the trigger needs between 0.5 microamps and 0.9 microamps as Darlington base current. So the discharge current flowing to ground has to be at least 0.9 microamps, and then the R2 resistor has to be less than 5 megaohms. Being the tail current around 80 microamps, the beta is between 90 and 160, which looks quite low to me, even considering that it is a PNP Darlington and one of the two transistors is a lateral PNP with a low beta. Write to me in the comment what you think about it. To understand the flip-flop in blue, we need also the output stage in green and the discharge transistor Q24 in yellow. The flip-flop is composed by Q16 and Q17 with base and collector cross-connected. Let's say the voltage across the capacitor is less than 5 V, Q16 is saturated and Q17 is off. 0.9 mA are flowing in this branch, and the same current is copied to this other branch of the current mirror Q19, providing enough current to saturate Q20. Since Q20 is saturated, a current is flowing in this branch. This current goes to R15, creating a voltage drop, which switches on Q24 and Q14, which start to draw currents. The limit of the current flowing Q20 is calculated assuming Q20 in saturation and this node at 0.7 volts. The current flowing in R15 is around 140 microamps. Moreover, considering Kelvin currents law in this node, we can write this relationship from which we get the base currents of Q24 and Q14. Knowing these currents, we find out that this node is around 0.8 volt and the current in R15 is around 170 microamps. Now we know the voltage across R11 because at this node we have 1.5 volts and this node remains at 0.7 volts. So the current through R11 is equal to that through R15, so it is equal to 170 microamps. The 100 microamps flowing through R11 go into the base of Q16, which has a collector current of 0.9 milliamps. The ratio 0.9 milliamps over 170 microamps is 5.3, so the beta of Q16 is less than 10, and we are sure that Q16 is forced into saturation, switching off Q17. If the voltage across the external capacitor is less than 5 volts, the trigger comparator provides an increasing current to Q15 up to 72 microamps. Q15 starts to draw current from the base of Q16, but at most it can draw 170 microamps, and the ratio between 170 and 72 is 2.3, much less than 10, so we are sure that the current coming from the trigger comparator is enough to force Q15 in saturation. If Q15 is in saturation, its collector emitter voltage is 0.1 volts and the Q16 is switched off, letting the base of Q17 going up to 0.7 volts. Now the current flowing in R10 becomes 0.86 milliamps and it goes into the base of Q17, forcing it into saturation, because its collector current is the same 0.86 milliamps copied by Q19 in this branch. Since Q17 is saturated, this node is at 0.1 volts, so even when the voltage across the capacitor raises above 5 volts and the trigger comparator doesn't provide any current to Q15, switching it off, the base of Q16 is kept low and the flip-flop remains in the same state. In this case, Q20 is off and the 555 output is high. When the voltage across the external capacitor reaches 10 volt, the threshold capacitor provides up to 4.9 milliamps. Being Q15 and Q16 off, the current starts to flow through R11, raising the base of Q16 up to 0.7 volt, switching on Q16. The current to the base of Q16 raises up to 4.8 milliamps. Being the collector current around 0.9 milliamps, Q16 surely goes into saturation, switching off Q17. Since Q17 is off, the base of Q20 goes high and Q20 starts conducting. We saw previously the base of Q20 reaches 1.5 volt and 170 microamps flow into R11, so now 0.73 milliamps go into the base of Q20, which has a maximum collector current around 2 milliamps, so the ratio is this, which is less than 10, so Q20 is surely in saturation. In this situation, the 555 output is low, Q24 and Q14 are on, the external capacitor starts discharging and the cycle repeats itself. When the voltage across the capacitor decreases below 10 volts, the threshold comparator stops providing current, but 170 microamps keep going into the base of Q16, keeping it in saturation. Now let's see the output stage working. It is composed by a Darlington NPN Q21 Q22 and NPN Q24. The Darlington provides up to 200 milliamps, but it produces an output voltage drop between 1.7 volts and 2.5 volts. The Q24 NPN sinks up to 50 milliamps alone and up to 200 milliamps with the help of Q23 in transdiode configuration to provide additional current to the base of Q24. The voltage drop is between 0.1 volts and 2.5 volts, depending on the current load. Q22, Q24, and Q14 are large BJTs with respect to the others because they need to provide large currents. Now let's see the situation in which Q20 is off and the output stage is providing 200 milliamps to the load. In this situation, the datasheet tells us that the output voltage drop is 2.5 volts. This means that 1.1 volts drops on R12 and the base current of the Darlington stage is this. So the beta of the output to Darlington is 1235, not too much for an NPN Darlington, but this is not surprising being Q22 a large transistor. didn't find the reason for the resistor R13 neither in the Camenzind book nor in the other documents, but I think it helps discharging the output Darlington in the transition from on to off. When the load requires less current, the output voltage drop is less, but of course never less than 0.9 volts. Now we see the low output state when Q20 is in saturation and Q24 sinks current from the load. In his book, Camenzind says that in the low state, Q24 receives sufficient base current to work alone up to about 50 mA. Beyond that, as the voltage drop increases, Q23 feeds extra current into the base circuit. From the datasheet, we see the output voltage drop with 50 mA is 0.4 volts, so Q24 is not in saturation and we get the beta of this transistor, recalling the base current of Q24 is around 0.6 mA. If we need more current, the output voltage raises reaching on Q23, which provides more current to the base of Q24, making the collector current raising up to 200 mA. If the collector current decreases around 10 mA, Q24 enters in saturation region. Now let's finish the circuit analysis with the Camenzind words. There are several flaws in this design, indicative of the early period of the IC design. Neither comparator is well balanced, showing offsets of as much as 30 mV. The circuit can get away with that because the voltage swing is quite large. The operating currents are quite large. The lateral PNP transistors run at up to 1 mA. That was acceptable at the time since the device had 10 micrometers geometries. Today it would be excessive. The output stage consumes a considerable amount of current in the low state, and during switching both output transistors are on for a brief period of time, producing a current spike in the supply. Despite the fact that much better performance is possible with more modern design techniques, the circuit is still being sold today in its original form. Thanks to CAN-Sheriff, we can show you the die of the chip. These three large transistors are Q22, Q24 and Q14, which must draw large currents. Here the NPN Darlingtons of the threshold comparator, and here, much bigger, the PNP Darlingtons of the trigger comparator. Here Q19 with its two collectors forming a current mirror for the biasing of the flip-flop and the trigger comparator, with the help of Q9. Here Q16 and Q17 forming the flip-flop. Please leave me a comment, let me know if you liked this video, make sure you put a thumb up, click the notification bell and subscribe to my channel.